We mentioned the idea of population proportion and how it's unknown to us, right? So our first goal is to try and gather some idea about it, like, what is it approximately? And we said p hat could be used as a good unbiased estimator of it. Okay, well, remember previously we took our first stab at a population mean, right, by constructing a confidence interval, and that's exactly what we're going to do here. But let's review the idea of a confidence interval. Okay, so I'm going to make a line interval. Okay, just a line. And then we said, okay, well, um, we can certainly always gather our population or our sample mean, sample mean. And then from there, we would go out some distance. We called it a margin of error. And that had a specific calculation. So that was E. And then on our number line, we would do X bar plus E. And then on the left side would be X bar minus E. And this space in between would be our confidence interval. And maybe it was a 95% confidence interval. Okay. And then when we wrote that, we had the understanding that, there's some level of confidence associated to it, and maybe the population mean was in there, maybe not. But the idea is that if we made, 100 of these 95% confidence intervals, and 95 out of the 100 would contain the population mean. Okay, same thing for population proportion. Okay, so the idea would be, okay, we're going to take a stab at the um, value of the population proportion using p hat. That would be a good first stab, a good estimate, right? And it's an unbiased estimator. And then from there, we would extend out some margin of error in both directions. Okay, give ourselves some wiggle room, and we'd have p hat plus e on the right side, and then p hat minus e on the left hand side, and then maybe by sheer happenstance of construction, and again, this might be our 95% confidence interval. Maybe this time in this construction we hit P, our population proportion. Great. Okay. So really, as I compare the strategies between what we did for sample means and or what we did for a mean and a proportion, they're very, very similar. What changes? Well, first thing, we use p hat instead of x bar. Okay, that's easy peasy. Okay. And actually what we're going to have to do is we're going to have to tweak the margin of error calculation due to the changing of the estimating variable. So instead of using x bar, we're using p hat. That's going to necessitate a change in our margin of error calculation. So let's dig into those details. Okay. A little bit. We'll mention more on exactly why we have to change it in the next video when we talk about tests of significance. It's easier to talk about it there. So previously we know this is how we calculated in a margin of error, right? The big differentiator here was whether sigma was known or sigma was unknown, right? And then we had different calculations. Z changed to a T, and same thing here. When we use Excel, we changed it from confidence.norm to confidence.T or vice versa, depending on the conditions we had, okay? So, okay, we know that it changed because our standard deviation changed, and it happens that with population proportions, our standard deviation changes again. Okay, you'll notice that we had the z alpha over 2, that's still the same. Sigma now changes to the square root of p hat times 1 minus p hat. Okay, a little bit more computation intense, but it's not bad. And otherwise, everything else remains the same. Okay, and so since we're using z, that's connected to the standard normal distribution, so that's why we have to use confidence.norm, and then we would use this command, so alpha would remain the same, sigma would change to our p hat times 1 minus p hat square rooted, and then n. Okay, so that's how things change. Why exactly, I want to discuss in the next video. Okay, so just to recap, I did not talk about conditions. These are really easy to satisfy, but we have to have a sample that's SRS, okay, or we can say it's approximately an SRS, okay, and we have to have a large enough sample size. So generally, at least 30 in our sample. If we do have strong skew or Outliers, we should check. Normality would be a better condition. So if it's normal, that's always okay. Otherwise, n greater than 30 is enough. Okay. And then our confidence interval is, what we saw above in the picture, p hat minus e, p hat plus e, where we calculate e, our margin of error according to these methods. Okay, so either longhand, so this would be the longhand, and this would be via Excel. Okay, so in short, this is how we do it. Why we have this specific margin of error? Stay tuned. I promise I'll explain. Okay, so example. You can read the instructions here, but the idea is we want to construct a 95% confidence interval for the proportion of patients in the United States that experience one or more healthcare associated infections. Okay, so I am just going to be lazy and I'm going to call all this that I'm underlining our P. Okay, that would be our population proportion. So I need to find, let's see, so I know the 95% confidence interval is going to look like p hat minus e, comma, p hat plus e. Okay, I know that. So I need to find p hat and I need to find e, right? And so e, well, an e, right, if I were to do it longhand, it would be z alpha over 2 times, and then square root p hat 1 minus p hat all over square root n. If I were to do longhand, I'm actually going to end up using Excel, okay? But to do this, I need to figure out what n is, right? N would be, okay, I need to just remember, so n is the total number of individuals in our sample. I'm reading the problem. Oh, that's the 11,000 number. 11,282. Okay, one piece of the puzzle solved. So then how do I get p hat? Well, p hat is going to be the number of individuals in our sample, so n, 11,282, okay? And then the numerator, remember the numerator would be the number in the sample with our desired trait. So how many have, so okay, what is the trait and how many have it? Well, it's going to be the same trait as what's present in the population proportion. So the trait is that experience one or more healthcare associated infections. Okay, so in our sample, how many experience healthcare related infections? Okay, reading 452, right? So that is the number that goes in my numerator. Okay, and then I can do the calculation, and I would say I get a number. Okay, I am going to switch over to Excel, but I'm just going to say do not round this. Okay, you really shouldn't be rounding anything until the very end. So if you're doing this by hand with a calculator, keep all the digits that your calculator gives you until the end. Okay, so now let's see. Okay, so I need to construct this. I'll get this ready for when I'm done with Excel, but let's hop over into Excel and do this there. All right, so I'm in Excel. I kind of have it set up. We will come back and do the test of significance eventually, but more on that when we get there. So we said that this was 452. Let me just confirm that. Yep, 452. And the total number in our sample, that was 11282. So then p hat, I can just do number with the trait divided by n. There we go. Okay, so I'm just going to use that whenever. And then now for the margin of error. Okay, so I'm just going to get my CI ready. So margin of error. I'm going to do confidence.norm. Alpha, so I'm making a 95% confidence interval. That means alpha is 5%. So I'm just going to enter, 0.05. Okay. Standard deviation. Now this is the weird one. You have to do a square root in here. It'd be square root, so SQRT. And then it's going to be p hat times 1 minus p hat. And I need to make sure that the 1 minus is in parentheses, order of operations, as always, is super, super important, okay? So again, the standard deviation I need to use is square root p hat times 1 minus p hat. And then the other thing I need is size, so that's the total number in my sample. And I should be good to go, okay? Cell referencing here, super helpful in case you make a mistake somewhere early on and then you have everything cell referenced and it'll auto update. If you type things in manually, you have to update it every place where you made that error, if you made an error. So moral of the story, don't make an error and you're good, okay? So there we go. We have our margin of error, okay? So then our confidence interval, the left boundary is going to be p hat minus our margin of error. And then our right boundary is going to be equal to p hat plus our margin of error. Oops, yeah, I added an extra parenthesis. Whoops, okay, there we go. So there we go, okay? So I'm going to go back and say that our confidence interval is between these two numbers. And there we go. Okay, so I just copy that over. And then remember, we have the two definitions for a confidence interval. Here are the two interpretations, right? So we have to first say something about the confidence interval that we made. Okay, so that one is we're 95% confident that the true population proportion of patients in the U.S. that experience one or more healthcare associated infections is in this interval. And then the second one is about the general repeating idea. So if we were to repeat this process and construct 195% confidence intervals, we would expect 95 of them to actually contain P. Okay, so again, capturing both ideas of the confidence interval is super important. Make sure to get them both. But this is a quick overview of, how to make a confidence interval with a population proportion. And again, the big idea that we need to take away here is that conceptually it's the same as what we've done in the past. It's just changing some of the mechanics, mainly changing the standard deviation to the square root of p hat times 1 minus p hat. Okay, and everything else should be good. Next up, testing with one sample for significance.